Good morning, everyone. Did you have a great night last night? My name is Yoshiaki Miyamoto, the chairman of the first session. The first session has 3 hours talk by Dr. Jeff Kepert. First of all, I'd like to introduce Dr. Jeff Kepert briefly. Dr. Kepert is known for his work in boundary layer dynamics in tropical cyclones. He received a bachelor's degree from University of Western Australia and a master's degree and PhD degree from Monash University. His PhD thesis is pretty famous for DC scientists, and it is entitled The Wind Field Structure of the Tropical Cyclone Boundary. During and after his PhD course, Dr. Kepert has published a number of novel researches that may be divided into 2 research fields mainly. One is data assimilation. The other one is tropical cyclone dynamics, especially in boundary. He works at Bureau of Meteorology in Australia for many years as a forecaster or researcher. And he's now the team leader of high impact weather team in Weather and Environmental Prediction Research Group at the Center for Australian Weather and Climate Research. He was a co-director of WMO7 International Workshop on tropical cyclones in 2010. And also he edited a science book. I think you may know the book, Tropical Cyclone Structure and Dynamics. We are grateful for his presence among us today. Please join me in welcoming Dr. Jeff Kepert.
Yes, thank you very much. As I said last night, it is very nice to be here in Japan, and I'm looking forward to a couple of days of good science discussion. I enjoyed last night meeting some of you and talking about the posters very much, so I hope we can continue that. I've given you all a copy of my card. I apologise, it's actually a bit out of date because it has my position as being in the data assimilation group, which I'm not anymore. But I've given it to you so that you've got my email address, and if any of you would like to ask questions about any of this work in the future, please feel free to contact me. So, the boundary layer, I thought it was good to start the talk by putting up just a summary of what we mean by the boundary layer. And this is taken from Keimer and Finnegan's book. It's the lowest 1 to 2 kilometres of the atmosphere, the region most directly influenced by the exchange of moisture, heat and water vapour. Turbulent motions on the scale of an hour or less dominate the flow, transporting atmospheric properties both horizontally but especially vertically throughout its depth. The mean properties of the flow, wind speed, temperature and humidity, have their sharpest gradients in the lowest 50 to 100 metres, which is called the surface layer. And turbulent exchange in this shallow layer controls the exchange of heat, moisture and momentum at the surface, and therefore the whole boundary layer. So we have this picture of a transition in the flow properties as you come down towards the surface. And one of the things we know that we see in the boundary layer is we see an increase in the cross-isobar flow component of flow towards the surface, and we expect to see a reduction in the wind speed towards the surface, for instance. In 1997, the Hurricane Research Division deployed for the first time a new instrument called the GPS drop sonde. And I'll tell you a little bit more about the drop sonde later, but here are 3 of the very first historical measurements ever taken by a drop sonde. And they featured on the cover of the Hurricane Field Program the next year, and I've put this up because it's a convenient place to show the position of the drop sondes. This was Hurricane Guillermo and the eye wall, And as the aircraft flew across the eyewall, it released one here, and one here. So these three dropsons were released within about 40 kilometres of each other, 40 or 50 kilometres. And if we look at the wind speed traces, so this is wind speed against altitude, they are really very different. The first one that was dropped, the red trace, it had a fairly constant wind speed, then a rapid increase in wind speed down to up to 70 metres a second, very near to the surface, and then an equally rapid decrease, and the surface wind was almost the same as the wind at aircraft level. The next one they released, which is the black curve, didn't show as much of an increase, but it had the same property that the surface wind was almost the same as the wind at flight level. These were very surprising. The third one looked more like you would expect. It came down, there were some wriggles associated with the turbulence, and then the surface wind was about 3/4 of the wind at flight level. So it's a very surprising result on a number of levels. One is there's no or very little evidence of frictional reduction of wind speed in two of these dropsons. The other one is that we're accustomed to thinking of the boundary layer as being horizontally quite homogeneous. In fact, a lot of the early boundary layer experiments, things like the Kansas experiment or the Wangara experiment, were done in very flat uniform terrain, precisely so that they could assume horizontal homogeneousness. And yet here we have two dropsons that were released 3 seconds apart. So they were released within a few kilometres, 3 minutes apart. They were released within a few kilometres of each other, the blue curve and the red and the black curve, and yet they have radically different structures. So one of the assumptions that we're accustomed to thinking of in a tropical cyclone boundary layer, that it's horizontally quite uniform, was shown by these observations to quite simply not be true. So the tropical cyclone boundary layer is a very important part of the storm, and there are a number of reasons for that. One is perhaps the most obvious. We live in the boundary layer, so if you want to understand the impact of tropical cyclones on humanity, you have to be able to understand the boundary layer. We live there, our structures are there. If you want to build buildings that will withstand cyclones, you have to understand the boundary layer. It's a key component of potential intensity theory, and we'll visit that idea tomorrow. It's very important to the ocean response. Cyclones can produce damage in a number of ways. We've seen rainfall damage as we drove up here yesterday, and of course we think of wind damage. But actually one of the most devastating forms of damage is storm surge, and that's a result of the cyclone pushing the water around. The most deadly tropical cyclone in history was the Great Bangladesh Hurricane of 1970, which killed between 300,000 and 500,000 people. Hurricane Katrina in 2005 killed 1,300 people, and in both cases the storm surge was responsible for the majority of deaths. So understanding how momentum gets from the atmosphere into the ocean is important. If we want to build structures to withstand cyclones, we need to understand the need, winds and turbulence, and something I'll touch on briefly tomorrow, it's actually part of the definition of cyclone intensity. So if we want to talk about intensity, it's important. So the structure of these talks, I've divided it into 6 chapters, which are not all the same length. And so the first session will be introductory, and I'll look at the observed structure. Then we'll move to 2 talks that will look at the dynamics of the tropical cyclone boundary layer and try and understand why we see what we do in the observations. And then tomorrow we'll look at thermodynamics, air-sea fluxes and turbulence, and the last hour or so we will look at the question of secondary eyewall formation and the boundary layer role there. Some of this work is These two parts of the talk are largely based on work that was in my PhD thesis, so that was done 10 to 15 years ago. The thermodynamics is new work that's not yet published. This is largely the work of other people, and the secondary eyeballs is subject to the paper I had out just a month ago. So there's a mix of old and new in here. If we look at the surface winds in a tropical cyclone, these plots are taken from a paper by Mark Powell, who has been one of the lead researchers in the field of tropical cyclone boundary layer. This is a study of Hurricane Frederick of 1979, and he did a composite analysis using aircraft and buoy data. Frederick was heading up towards the Gulf Coast here. And we see in this image things that have been, in fact, quite well known at the time and has been seen in many other observations. But the strongest winds are in the right forward quadrant, weakest winds to the left rear. That's very familiar. It was actually first discovered in the 1850s. If you're interested in historical documents, there's a very nice book by Henry Pittington called The Sailor's Hornbook or Law of Storms, which was written in 1848, and you can find it on Google Books for free. The other panel here shows the inflow angle, and this is perhaps less familiar. To the right of the storm, the inflow angles are in the range of 40 to 50 degrees. To the left of the storm, there is substantially less inflow. There's sort of 0 to 10 degrees. In fact, there's a patch in here where there's net outflow, so the surface wind vectors are actually heading away from the centre of the storm. If you average it around the storm, the mean inflow angle at the surface is typically 20 to 25 degrees. These observations are from a typhoon in 1938, I think it was, 37 or 38, and were actually taken by the Japanese Navy. I put them up not just because we're in Japan, but because until the GPS drop sonde came along, these were actually the best ever measurements of the surface wind field in a typhoon at sea. And what happened was the Japanese Navy was on a training exercise and they got caught by a typhoon which passed northwards to the east of Japan, and these individual dotted lines here are individual ships. Arakawa, a famous name in meteorology, wrote this up originally in a Japanese journal, and then it was published again in Monthly Weather Review in English in 1953. This was quite an asymmetric storm because it was undergoing extratropical transition, but in his composite analysis we see similar features. So here's the centre of the storm moving almost due north, and we have the strongest winds on the right-hand side and weaker winds on the left. Quite an asymmetric structure in the streamlines because of the extratropical transition. This was actually to me has always been a very impressive set of observations for the sailors to have had the discipline to keep taking observations while a major typhoon was passing across their fleet. If you have a look at the paper, there are some photographs of the wave field, and I think it must have been very hard to collect these observations. Here's the plot of the wave field, and so the centre of the cyclone here, and the significant wave height is getting up to 10 metres on the right-hand side of the track. Very strong asymmetry with relatively lower winds of sort of 7 to 8 metres on the left of the track. More observations of the wave field. These were done by more modern technology. This was using a synthetic aperture radar, a scanning radar altimeter mounted on aircraft, and is in Hurricane Bonnie. So the middle plot here shows the significant wave height, about 10 metres on the right of the storm, about 6 on the left. The storm is moving in about this direction. And these plots show the directional wave spectrum at various locations around the storm. On the right of the storm, where the highest waves are, the spectrum is quite simple. There's a single peak, and the waves are propagating, but essentially in the local wind direction. These arrows show the wind direction at the location. And the waves are, and there's single peak, and the waves are quite large. As we move around to the left of the storm, we get more of a displacement between the wind direction and the wave direction becoming quite prominent here, and we start to see a second spectral peak. If we get round to the left rear of the storm, the seas become quite confused. We actually have two major peaks and of waves which are heading in opposite directions, almost opposite directions. So you can imagine that having those counter-propagating wave fields would be very difficult for a ship. The reason the waves become so complex is the flow is in this direction and the cyclone is moving in this direction. So on this side of the storm, as the cyclone moves along, the ocean surface really only sees winds from one direction, and the waves can build up due to a resonance between the propagation of the cyclone and the propagation of the waves, and you get quite a simple wave structure. On the other side of the storm, it's more complicated, and if you were at one point on the surface, you'd see quite large changes in the wind direction, and as a result you get a very much more complicated wave field over this side of the storm. I won't talk very much more about waves in this seminar, but if you want to know more about the intricacies of it, this is quite a good paper to look at. One of the ideas that's been used a lot to understand or to try and quantify the effect of the boundary layer in a tropical cyclone is the surface wind factor, and we'll talk about this a bit more in subsequent parts of the talk. But the surface wind factor is simply the ratio of the surface wind speed to that at some higher level. So you might have, say, aircraft flight level winds, which are at 850 millibars or 700 millibars above the surface, and you have some surface wind observations, and you simply calculate the ratio. The idea was used for many years with aircraft reconnaissance. If you wanted to estimate a surface wind, they'd simply measure the aircraft wind and then multiply by 0.7 or 0.8, and they'd say that was the surface wind. And that value of 0.7 to 0.8 was very, very widely used. It was also used if people wanted to parameterise cyclone winds for, say, a storm surge model. They could get a parametric model of the gradient winds and calculate, simply multiply by 0.7 or 0.8. There was a very poorly known but quite important paper in 1988 in the Journal of the Meteorological Society of Japan, and this paper had several examples of wind observations from flat coral atolls to the south of Japan. And what Mitsuda et al. Had done was they had taken pressure observations and wind observations from the atoll, and as the cyclone went past, they were able to calculate the gradient wind, which was this curve here, and then they had actual wind observations, in this case from 4 atolls, and they found that the wind observations were somewhere around 0.6 to 0.7 of the gradient wind, which was consistent with what we expected, until they got inside the eyewall. And when they were inside the radius of maximum winds, they found that the surface observations were actually almost the same as the gradient wind, We saw that in the first two of those dropsonde observations I showed, where the surface wind was almost equal to the wind aloft. The lower plot shows just the innermost 70 kilometres, and so here is the gradient wind speed, and here's the surface azimuthal wind, which becomes equal to or slightly greater than the gradient wind in near the centre. The ratio goes from about 0.6 most radii to more than 1 inside the eye wall, exactly as we saw in the dropsonde observations. And they also showed a radius plot of the inflow component, and that increases to a maximum near the radius of maximum winds, and then it decreases again as you go inwards. More modern observations showing essentially the same thing. These are from a paper that Mark Powell, Eric Gilhorn and I had a few years ago, and these were done using an instrument called the step frequency microwave radiometer on the reconnaissance aircraft. So what we have here is the plane is flying through the centre of Hurricane Katrina from east to west. We have the flight level winds, which are recorded directly by the aircraft, and then we have the remotely sensed surface wind speed from the SFMR instrument. And you can see very much like the calculations that Mitsuta et al. Had done. We have a ratio that's somewhere around 3/4 in a large part of the storm, and then as we get just inside the maximum winds, the surface winds become essentially equal to the winds at flight level. The ratio sitting around about the 0.6, mark, and then it becomes 1 in at the eye wall, in the eye, sorry. The other thing that we know about the surface wind factor is we know that stability structure, or we know that the stability has an important impact on boundary layer structure. And we see that because in stable conditions you damp the turbulence out, and therefore you get less mixing of momentum down towards the surface. So the surface wind factor has a dependence on the air-sea temperature difference. This is from a paper by Mark Powell and Pete Black. Pete has been one of the other people who's been very prominent in cyclone boundary layer meteorology throughout his career. And the average value is about 0.7, but when we have unstable conditions, so the sea is warmer than the air, we get additional mixing, bringing momentum down to the surface and giving us stronger winds. Stable conditions, we have the opposite effect. I might pause a little and just ask for any questions, because one of the things I'd like to happen is that you actually interrupt. Okay. I'm trying to get you in the habit of interrupting me when you want to know something.
I have a question. I think it's very difficult to define, the level, not the surface level. So in these cases, what is the definition of to calculate the level, to calculate gradient wind?
Yes, that's a good question. People have used different levels over the years. In the case of sometimes people use a calculated gradient wind, as Mitsuta et al. Did, because they didn't have upper level wind observations. Papers like this, they've tended to use the flight level winds, which are typically either at 850 hectopascals or 700. The reconnaissance aircraft used to normally fly at 850 hectopascals in weak storms, and then as the storm intensified and became a bit more dangerous, they'd fly at a high level for safety reasons. But I think when in this paper they'd actually combined data from the two levels in calculating the surface wind factor. So it wasn't until a little bit later in a paper that I'm going to talk about next that it was realised that it was actually important to keep track of which level you were working from. Anyone else? So we've talked about the horizontal structure. We've talked about the difference between the winds at the top and the bottom of the boundary layer. And we'll now spend a little bit of time looking at the vertical structure of the boundary layer and how the wind varies throughout the depth of the boundary layer. So these are figures from one of my 2006 papers in the Journal of Atmospheric Sciences. These are in Hurricane Mitch. Mitch was a very strong storm that was Category 5 at the time of these observations. It was only 80 kilometres off the coast of Honduras, but was moving extremely slowly, and it took another day and a half before it actually made landfall. And it was a late October storm, so there was only one research mission flown into Mitch because it being late in the season, Hurricane Research Division had already spent a lot of their research budget, and unfortunately they could only afford one mission. But they released over 30 dropsondes during that mission as they crossed through the eye of the storm. And what I've plotted here is the azimuthal and radial mean wind. So I took the dropsondes and divided them into bins according to distance from the centre of the storm, and then calculated the azimuthal and radial mean for each bin. So if we look at the azimuthal winds first, near the centre of the storm, in the innermost 15 kilometres, we've got virtually constant winds with height. There is a very faint hint of a frictional retardation in about the lowest 200 or 300 metres. From 15 to 25 kilometres, which is sort of on the inside of the radius of maximum winds, we have a very marked, very strong 75 metres a second wind maximum very close to the surface, only 300 metres up. And then quite rapid decrease in wind speed aloft. On the outer edge of the radius of maximum winds, we have quite a dramatic change in properties. The wind maximum is a little weaker. It's about 2 or 3 times as high, and the reduction in wind speed aloft is not as strong. And then if we go out to the outer part of the vortex from 40 to 100 kilometres, we see more what you'd think is a classic friction layer with a steady increase in wind speed as you go up. If we look at the radial flow, the blue curve in the centre of the storm, there is almost no cross isobar flow. The flow is almost perfectly circular with no inflow. On the inner edge of the eye wall, which is the green curve, we have very strong inflow, about 30 metres a second, which was unusually high in the case of Mitch. The inflow layer is about 1.5 kilometres deep, and above it we have quite strong outflow, and this is axisymmetric outflow. This is averaged around the storm, and it's getting up to 5 to 10 metres a second. The 25 to 40 kilometre annulus is similar, strong inflow with outflow aloft. And then as we get to 40 to 100 kilometres, the inflow is somewhat weaker, and we see the decay of the outflow layer aloft. So the strongest inflow is near the radius of maximum winds. Again, we saw that's similar to what we saw in the Mitsuda et al. Observations, but we have this really quite dramatic region of outflow above. James Franklin had a quite important paper in weather and forecasting in 2003, which was averaged over a large number of storms but showed a broadly similar structure. So these were drops-on data. He's normalised by the flight level wind speed, which was 700 millibars in the case of all of these observations. And he's taken over 200 observations in the eye wall of a large number of storms and about 120 in the outer vortex. And we see that in the eye wall we have a very pronounced wind maximum. It's about 20% stronger than the flight level winds. It's at about 500 metres height. In the outer vortex, the wind maximum is less pronounced and less strong and higher. We can also read the surface wind factor off this chart because they've been normalised to 700 hectopascal wind. So the eye wall, the surface wind factor averages a little bit over 0.9, and in the outer part of the vortex it averages a little bit under 0.8. Again, that's quite similar to what we saw in Matsuta's observations. And James Franklin and his co-authors came up with some recommended wind adjustment factors, and these have actually been used in operations by the United States ever since. And he had a table which had a couple of different conditions on. If you're in the eye wall, these values were recommended depending on what level the aircraft had flown at. They were generally somewhat higher than were recommended for if you were in the outer vortex, and he had separate tables depending on whether you were in convection or not in the outer vortex. So some of what we're seeing here is probably a reflection of the warm core of the cyclone. The gradient winds do decrease as you go from 850 to 700 millibars, so the reduction factor should increase. But it's also partly a reflection of boundary layer dynamics, the differences between the eye wall and the outer vortex. We'll look at that in some more detail and why that occurs later this morning. The other thing that was in Franklin et al.'s paper, which has been, I think this is a very important figure, and I think it's also been somewhat neglected over the years. He had 7 hurricanes where there was enough data in the eye wall to do an eye wall mean wind profile just for that hurricane. So here are their names and the number of drop-ons, and these again have been normalised by the 700 millibar wind, so they're all normalised back to unity up here. But there is enormous amount of variability from one storm to the other. Dennis, the strongest winds were 30% stronger than the winds at 700 hectopascals. And in contrast, Lenny, they were only 10% stronger. We have storms like Brett, where the wind maximum was down at 300 metres, and we have storms where it was at 500 metres, or perhaps even Bonnie, where it was up at 700 or 800 metres. The surface wind ratio in these storms varied between 0.82 and 0.96. So it was quite a large amount of variation from one storm to the next, and Franklin et al. Actually speak of the character. Yeah.
Is this statistically significant?
That's a good question. James didn't put in any statistical tests. Some of them it probably is. Some of these have got 20 or more observations in, and they were certainly Dennis, Floyd, Mitch and George, which I've looked at the data in some detail. They were evenly distributed around the eyeball, so they were good, they were probably good azimuthal means. If you look at individual drop-song profiles, there's usually quite a bit more noise in them, which is due to the turbulence. We saw that in the observations from Guillermo. So I think these differences, without having actually done t-tests or something on them, I think these differences are real. Do we have any other questions before I continue?
I have one question. One slide before. Sorry. From this figure, we see the small number of the substring factor, the 925 × which is minimal, which height is minimal. The simple imagination of this factor should be increase because decrease. So,
I think there's two reasons we're seeing quite a consistent number there. One of them is that 925 hectopascals is quite low, so it's probably below the wind maximum, and so you're looking at perhaps somewhere around here in the storm. I think that's one reason for the difference, but the other reason is to do with the way in which the observations are taken. Now, I mentioned a minute ago that the level at which they fly into storms depends on the intensity. Nearly all the data at 920 at these lowest two levels